The problem we're looking at now is where we have a rod. It's insulated at the ends, so it looks something like this. When I say, sorry, it's not insulated at the ends, there's heat sources at the ends. So for example, we're talking something like temperature left, temperature right. And there is also a time aspect here. So there's some initial temperature distribution when you eventually go into solving partial differential equations, or maybe even what I write down might be familiar from Marina's classes. So if x is the distance along the rod, you're looking at the temperature at a distance x at time 0. So this is now a function of two variables. Will be given as some function of x. So this is something similar you may have seen in Marina's class in a slightly different context. Typically, in fact, well, in this module, certainly, in particular, this will actually always be 0. We'll even throw it out there. So you have a temperature on the left, a temperature on the right, and they're fixed and they're heat sources. But the initial temperature, so this is like an initial temperature of the rod is 0. And what happens is, certainly if the heat sources are above 0 degrees, you will get heat flow from the right into the rod, from the left into the rod, and eventually this will kind of reach equilibrium. So this we have here, we have an rod, a rod, insulated except at the ends where it is in thermal contact with heat sources. How does the temperature in the rod change with time? This is the question. So you derive a one-dimensional heat equation. So we're going to do this. This part is theoretical background, background theory. In my opinion, it's probably good to go through it to help kind of your understanding of thermal physics, but in terms of it won't be examinable. So this is a function of two variables. So you get the temperature at each distance along the rod and at time. So basically you have that the rod is heating up, as it were. So what we're going to do is we're going to mesh the rod into equal length pieces. We're going to chop it up. Now we don't really push things even in the lab, because I don't examine it in the lab. But if you were in the lab, like, you'd probably make an array and like cut it into possibly 20 pieces. I'm not sure. But we'll typically maybe just cut it into 4 pieces or 3 pieces. And we will approximate the temperature at these 3 points. But of course, those 3 temperatures are changing in time as well. You're going to cut the rod into pieces, and we're also going to cut time into pieces. So there'll be a kind of diagram for that. And we're going to approximate the partial differential equation, this thing, at each node in the mesh. So it'll be a two-dimensional mesh. Like with the plate, you had distance, horizontal distance, vertical distance, horizontal mesh. We're going to have distance and time. We're also going to have a horizontal mesh. And each node, we're going to approximate the partial differential equation with finite differences, and we'll get simultaneous equations. But the way we do it, the simultaneous equations are going to be so simple. It's going to be very easy to solve them. Like, it's they're going to be hilariously easy to solve as equations. It'll actually end up looking more like Euler's method. And then using the theory, so the theory would say, and we'll get into this, but basically just kind of looking ahead, the theory says that in equilibrium, the temperature doesn't change in time anymore. So that blue thing is 0. And so you're left with a constant times a second derivative is equal to 0. And the question for you to think about, what curve has a second derivative of 0? And that tells you what the equilibrium is going to be. It's just written down there. What has a second derivative of 0 is a straight line. So this is kind of what the solution would look like. This is a 4.8 meter rod. So the x goes from 0 to 4.8. The heat sources are 20 and 80. You can see on the left is 20, on the right is 80. The curves are done by Excel. We actually only produce a few. So this is the initial one. is the blue one. So this, for example, is our approximation to the temperature at 3.6 at time 0. And then the red one, this is after 5 seconds or 5 time units. I'm actually not, yeah, 5 seconds, 10 seconds, 30 seconds, 60 seconds, and then if you let time go to infinity, it reaches equilibrium, the straight line up the top. So these are the numbers that we have. Now we have actually, this is done, I think, in VBA, so you get way more numbers. We're actually going to just go do 2 time steps in the written assessment. Okay, so this is what we're looking at. Okay, so a bit of background theory. So I'm going to indicate in the description of the YouTube video when this starts, and if you want, you should skip it. Sorry, if you want, you can skip it. I actually recommend going through it for your thermophysics. There should be some good stuff in there. Okay, so let's have a look at our problem. So this is the setup we had. We have a one-dimensional thin rod. The purpose of the thinness is that if you have a kind of an ordinary rod with some genuine extent and thickness, there's also an effect of, you know, if you look at the cross section of the rod, how does the temperature vary across the rod? That's a question which we're not really going to worry about. My line, am I right? Yeah. So, yeah, this is all we have at the moment. Now, what we're going to do is we're going to chop this thing up. And when we chop it up, I'm going to have to recalibrate my cursor. So you may or may not notice the picture changed. Okay, so you chop this up into pieces. So in theory, it really should be quite small pieces. And even though actually, yeah, so actually forget about what I said. So just really take a really small part of this. So consider this really quite thin. Now let's kind of blow that up. What we're actually going to assume about this rod is that it's actually kind of square, and you might say, how is it square? Surely it's round or whatever, but because it's thin, it doesn't make much of a difference. So we're looking at, we chopped a little piece. It's a really thin kind of little piece of it, something like this. And this width is delta x, I guess. Delta y can be the height, and delta z could be the depth. So this is a delta V. This is just a little piece of the rod. Now, when it's in steady state, it's quite easy. What happens is, say, for example, if it's kind of hotter over on the left versus on the right, in general, basically you're looking at a heat flow from left to right. Not exactly, because actually it started at temperature 0, but in general. Okay, so where it's drawn, if that little volume element, if that's initially cold or whatever and it's hotter here, you're going to get heat flow from left to right. So what you're going to get in equilibrium is that you've got a heat flow going in this face and a heat flow going out. Now for equilibrium, these have to be equal. If they're not equal, say for example, if the heat going in is bigger than the heat going out, then the amount of heat in here is increasing. And when the heat in the volume element is increasing, the temperature is increasing as well. And that's not indicative of equilibrium temperature. Equilibrium temperature is when the temperature does not change in time. So we're not getting that unless the heat flow in equals the heat flow out. Now we're going to say that the heat energy transfer per unit area will be Q of x, and then the heat out is Q of x plus delta x. So here this is supposed to kind of represent the point x along the beam, and then this other point is x plus delta x, and Q is this heat energy transfer in unit time. So we do energy per unit area per unit time. So if you multiply that by the area and the time, you get the heat in. And then on the other side, heat energy per unit area per unit time times area times time, and you get exactly the heat out. So you get heat in equals heat out. So this kind of a calculation is, you write something down, and what you can do here is you can divide both sides by the delta V and the delta T, and you end up with this thing here. Now this looks a little bit like a derivative, so this is to resemble, say, f of x plus h minus f of x divided by h, of course, but it's, yeah. Now what you want to do to make this all more accurate, you take the volume element to get smaller and smaller and smaller. I guess really what you're doing in terms of making the delta V going to 0, you can't really shrink the delta Y and the delta Z, but really what you're saying is delta X going to 0, which implies that delta V goes to 0, and this gets more and more accurate. And if you do delta V going to 0, which means delta X going to 0, you're looking at the limit as delta X goes to 0. So this equation here becomes more accurate. So this is kind of approximate, but if you do the limit, it gets more and more accurate. This must equal 0, and of course this is nothing but the partial derivative. Now, what's not really included here is some assumptions that actually the heat flow, we won't kind of get too into the weeds here, but really what this thing is we kind of assume, because the rod is thin, really you're talking about the heat flow at a point. It depends on x and also the y and the z. So really the heat flow depends on 3 variables, and if only one of them is changing and the others are kept constant, that's a partial derivative. But what we kind of assume basically is that the heat flow across this face is basically given as the midpoint, the mid y and the mid z. That's an assumption that's probably not really in the mix, and probably does need to come in here as well, but we won't worry too much about that. This thing is a partial derivative. I guess we're only interested in x changing. So this here is a partial derivative. And of course we want this to equal 0. So this is the equilibrium situation. Now we've Fourier's law. Now what Q1 here is, I guess, what the hell is this? I'm not sure. It's Q1. What this is kind of representing, I guess, is Q, I guess, should be a vector. And I think the notation I was going for here is it's Q1 in the I direction, and the I direction is the direction, that yellow arrow, and then whatever else you have there. So it's saying here that the heat flow is proportional to the temperature gradient. This probably is something we did in the previous section. Yeah, it's basically just saying that when there's a difference in temperature, that's when heat flows. So now that's Fourier's law. I think this is Fourier's law. Oh yeah, so we have partial Q, and really this is kind of Q1 is what it's kind of saying. We can, I mean, the thing we wrote down was this really. So we're looking at partial Q1, partial X. I guess we're differentiating both sides of this thing, aren't we? Partially. Yeah, we get minus K times the second derivative of this. This is just Fourier's law, but here we just showed that this partial derivative is 0. So actually what we've shown is that this constant times the second derivative is 0 when we're in equilibrium. So divide both sides by K and multiply both sides by -1. We have just derived the one-dimensional Laplace equation. So this is now we've already seen this with x and y, and this is just with x. So this is the equilibrium temperature for the rod. So the solution to this is very, very easy, because what is the second derivative of 0 is a straight line. Remember, second derivative tells you how the slope changes, And if the second derivative is 0, it's saying the slope doesn't change at all. And so, well, what's the curve that the slope doesn't change at all? That's a straight line. Now we do know that at 0, the temperature, say, is TL, temperature, right? And so L here is not a good choice. T1 and T2 aren't good either. I think maybe T0 and T final, even there, that isn't great. I keep getting caught by this. Like, look at the two symbols. It's not good. It's not important really, but let's say 20 and TF. And if it's in equilibrium, this is a straight line. That should be a straight line. This should be T0, not initial in time, but initial in distance. Okay. And we, you know, once you draw the picture, it's very easy to write down the equation. That I mean, I can even, it's actually possible even in this abstract setting to do this. So you're doing y equal to mx plus c. The m is the rise over the run. Now, because this is going down, we know it's a negative slope. The rise is the difference in temperatures, which is T0 minus Tf. And the run is the length of the rod. So that's the slope times x, and c is where it cuts, which is T0. So even in this setting where it's totally abstract, it's not too difficult to write down the equation of the line. Okay, so this is very, very simple situation. Now, we would have done this with boundary value problems. We would have had a bit of curve and the air temperature came in, but these rods are insulated along the entire beam. Okay. Now, suppose that the rod isn't in thermal equilibrium, but is actually heating up or cooling down. The temperature at each point is still changing. Now, what is going to happen here is we're going to have a net flow into the volume element. So again, I think this depth is delta z, this height is delta y, the width of this element is delta x, and we're talking about a net flow in. Now here we're kind of saying this is q of x. I guess it's so thin it can't really go in any other direction. And then this is q of x plus delta x, without looking below this, what we're dealing with. Now heat energy, so this is how much energy is in this volume element. So it's the mass of the volume element times the specific heat capacity times the temperature in Kelvin. So if you're talking about a change in heat energy, we're looking at something like this. So we've got the heat in minus the heat out. So this is a change in heat energy, and where are all these numbers coming from? Where it's dealt? So let me see. So heat energy, we should be looking at something like mass, specific heat capacity, temperature. The mass doesn't change, specific heat capacity doesn't change. So the change in heat is directly related to a change in temperature. So here's the temperature, change in temperature. Here's the C, and this other yoke must be the mass. So we see the volume times the density F. So this is our little equation. What's our little equation? This thing. So it's saying the heat in minus the heat out is equal to a change in heat, and a change in heat, the heat is directly proportional to the temperature. So a change in heat will cause a change in temperature like this. And here you kind of understand this specific heat capacity is bigger, the change in temperature is smaller. And that's the kind of role of specific heat capacity. We divide both sides of this thing by delta V delta T. And what we see is we get a delta X in the bottom, delta Y and delta Z's are gone, the delta T's are gone. And what about over here? Well, the delta X, delta Y, delta Z are all gone. The rho C remain, and the delta T gets divided by delta T. And then to make this more accurate, you take limits as delta X goes to 0 and delta T goes to 0, and you end up with the following. So this thing here, it's like f of x plus h, but the wrong way around. So this is a minus partial q partial x is equal to rho c partial temperature partial time. And then we use the fact that this thing here is equal to minus a constant times this should be the distance. This should be partial t partial x. You end up with, and the constant proportionality is minus k. So this minus kind of gets turned into minus k, which is plus k. This thing gets turned into, so if you differentiate both sides of Fourier's law, you get that this partial derivative is the second derivative of temperature. With respect to distance, we saw this previously. And then on the right, well, where the hell is rho c going? We might have to do some messing around here. What was our k before? Yeah, so this rho c has disappeared, so I guess we need to this is probably, to be honest with you, divided by rho c, and then maybe we'll call this thing k dashed, not a derivative, just a different k, and then k dashed divided by rho c is what we call k. I guess that's what's going on here. So this is where did this equation come from? The heat flow in minus the heat flow out is a change in heat, and there's a direct proportional relationship between heat and temperature. So this change in heat causes a change in temperature, and this just falls out. Now, there's a little comment there. We saw this thing in the boundary values. Where is this coming from? Basically, you have a change in temperature. You get the normal heat equation, but also some Newton cooling as well. Okay, so this is the derivation of the heat equation. I think that's where we'll leave this video.